Good morning, everybody. Going to give people a couple minutes to tune in before we start.
Yes.
Good morning, everyone. Going to give people a minute or two to join. Minimize this. All right, let's start chapter 19. Okay, so this chapter, chapter 19, is all about vibrations and waves. So let me just touch on some of the interesting things we're going to cover in this chapter. So one, let me just draw on this. Draw. Let's use green. So this is chapter 19, and chapter 19 is all about vibrations and waves. So we're going to start with just a little general description of what a wave is. And then going to look at, there's generally two different kinds of waves that we talk about. One, it's called transverse waves. And these are just sort of the waves that you're probably used to thinking about. These are waves like water waves, waves on a string, things like that. The other kind of wave is what's called a longitudinal wave. And a longitudinal wave, sound is a perfect example, or moving a slinky back and forth that we'll look at. And then in terms of a wave, we have different things that we use to describe a wave. So I'm looking at just an object. I might describe the position of the object, the acceleration of the object, the speed of the object. In terms of waves, there's four main things that we look at. We have the amplitude, wavelength, frequency and period, and wave speed. And then we're going to look at the fact that waves can undergo something pretty cool called interference. And when I have two waves that exist at the same place at the same time, they can affect each other, and they can either produce what's called a bigger wave, called constructive interference, or a smaller wave that can actually, waves cancel, and I can have destructive interference. And then we're going to look at Doppler effect and bow waves and shock waves. So chapter 19 and chapter 20 are very similar. I'm going to end up doing the chapter 19 and 20 homework at the same time. Oh, let me think about that. But anyway, chapter 19 and 20, we're going to have a quiz on both chapters at the same time. And that'll probably be the last material we cover before our first celebration. So let me do a new share for a second and just show you a quick example of a wave. All right, let me move this, types of waves. So can everybody see this new screen? Actually, let me just stop this share for a second and do a new share screen. Okay, so one, both types of waves are shown, and I'll be specific when I show you a PowerPoint slide in a second, but in a transverse wave, unfortunately I can't draw on this. Here, actually this is a standing wave, sorry, traveling wave. So these are both waves that are moving to the right, but first case we have what's called a transverse traveling wave, and that's one in which the motion of the wave in this case is to the right, but the disturbance that the string in this case is moving is up and down. Whereas on the bottom, what's called a transverse wave, and that's one in which the disturbance is along the same direction of the direction of travel. So just wanted to show you that real quick. Let me go back to this PowerPoint slide. So actually I have a quick question for you. Waves are extremely important in physics. If you had to guess how much of the information you get every single day, you get in the turn in. I need more coffee. All right, the question is, how much information, what percentage of the information that you get every single day do you think you get in terms of waves? How much of the information, what percentage of information that you get every day is in the form of waves? And the answer is about, what do you think? Jacob?
Definitely pretty high.
Pretty
I'd
high.
say. Pretty high percentage.
I've heard different things. What I hear is about 90%. So anything we see, light, we're magnetic wave. So anything we see, we're receiving that information in terms of a wave, a light wave. Anything that we hear is basically coming to us in the form of a sound wave. And so most of the information we get every single moment of every single day comes to us in the form of light and or sound. Okay, so first let's just talk about all waves are created by something which is oscillating up and down. So let's just be specific about something that's oscillating up and down. So I want to go to this again, and not transverse waves. Okay, so an oscillation is just something which is moving back and forth, to and fro, up and down, about a sort of what's called an equilibrium position, which is where, so like in this case, let me pause this. Can I move this at all? No. So if I had a spring, and again, I wish I had brought all this equipment back from the lab, but if I have a spring and I just attach a mass to it and pull it and let it go, this spring is going to oscillate up and down. So what we call an oscillation is really just sort of a repeating back and forth motion or to and fro about some equilibrium position. And this is sort of where the object wants to be when it's at rest. And then I pull it down and I let it oscillate up and down. That's basically just called a vibration or oscillation. So something which is oscillating up and down. Demo, move marker up and down on the board. So if I was teaching this in class, I would just say, look, if I just took a marker and I just moved it up and down and up and down and up and down and up and down and up and down, actually what I didn't want to do was move it. So if I just stayed where I was and just oscillated something up and down, that would be a vibration or oscillation. Now, I really love the definition of a wave, because what is a wave? How is it defined? It's just defined as a traveling disturbance. So in sound, sound is a disturbance of air oscillating back and forth. Light we'll talk about is sort of interesting. It's oscillating electric and magnetic fields. But in a wave, one of the things I'm going to mention, which is really important, is one, all waves are created by something which is vibrating or oscillating back and forth. So in the terms of sound, all sound is created by something which is oscillating back and forth. And we'll get to this in chapter 20. But this oscillating back and forth causes the air molecules to either move closer together or farther apart. And sound is really just a pressure wave which is traveling through air. But one of the important things that we're going to look at is, in a wave, the disturbance is traveling, but the medium does not. The medium just oscillates back and forth. So I haven't tried this before. I want to see if I can share a PowerPoint slide. So bear with me for a second. Hey, do you guys see a PowerPoint slide right now? Yep. With a transverse wave, which is moving to the right?
Yep.
Excellent. Okay. So a transverse wave is one in which the disturbance is perpendicular to the direction of travel of the wave. So like in this case, how would I create a transverse wave? Well, if I had a string or a slinky or something like that, and I started oscillating it up and down, one, the disturbance is the direction that the, in this case, the slinky is being disturbed up and down. But the direction of travel of the wave is the direction that this pulse is moving. So if in this case, the disturbance is moving up and down. So if I were to look at like one piece of the string, it just moves up and down, but the direction of travel of the wave is to the right. And in terms of the medium doesn't move with the wave, it just oscillates up and down. So if I were to look at, let's say, one of these dots over here. Oh, I can roll on this. Excellent. So let me, I didn't even realize that. So if I were to look at, let's say, one little dot here. One, this wave is traveling to the right. But if I were to look at any one single dot, all that dot does is just oscillate up and down. It's not moving along with the wave. The wave is the disturbance in this case, which is traveling to the right. I'm sorry, the wave is the traveling to the right, but the disturbance is just up and down. That's different than a longitudinal wave. A longitudinal wave is one in which the object is disturbed in the same direction that the wave is traveling. So for a longitudinal wave, if I had a slinky and I could move the slinky back and forth, that would send what's called a longitudinal wave. So in this case, if I look, this slinky is being disturbed horizontally left and right, and the wave is traveling to the right. So that would be one in which the disturbance is in the same direction of travel as the wave. Now this, I'm going to show you this animation again once we get to chapter 20. This in essence is how all sound is created. So you have some object here which is oscillating back and forth. If we're talking about our voices, what it is our vocal cords oscillating back and forth. We're talking about a speaker. All speaker is just like a little paper diaphragm that oscillates back and forth and sends a disturbance through the air. So what happens is your vocal cords or something are oscillating back and forth. It causes the air to get compressed together and then expanded apart. And what I really like about this animation, look at it for a second. It looks like you have a bunch of dots that are moving from one end to the other. But take a second and focus on any one dot. And what you'll see is that dot just moves back and forth. It's not traveling to the right with the wave. It's just constantly bouncing back and forth. So, I mean, it's hard to do, but you know, if you were to pick one little dot here, whoops, can I pick a dot? Oh yeah. If you were to look at, like, see this one dot here, all this dot is doing is moving back and forth. Even though it looks like I have a bunch of, let's say these are atoms of air moving to the right, any single atom just oscillates back and forth. So let me show you that one more time a different way. Let me share this. Types of waves. Okay, so here are the two different waves presented at the same time. So the top wave is a transverse wave. So here, this is just marking one location on the string. So let's just say this is a wave traveling on the string. The wave is, I should start doing this the other way. The wave is traveling to the right in this case. But if I look, any part of the string is just oscillating up and down. It's not actually moving to the right along with the wave. That is a transverse wave, one in which the disturbance, in this case, which is moving up and down, is perpendicular to the direction of travel of the wave. On the other hand, a longitudinal wave is one in which the object is being disturbed along the same direction the wave is traveling. So here you could kind of see the wave is traveling to the right. But again, if you were to look at any one part of this, let's say it's a slinky, then all that is doing is oscillating back and forth. It's not actually traveling along with the wave. So new share, go back to, nope, new share, go back to lecture notes. So when I say the disturbance travels, but the medium does not, the disturbance, the wave is this sort of disturbance which is moving through space, but the medium is just oscillating either up or down or back and forth. It's not traveling along with the wave. So for example, when I'm talking, it's not air that's coming from my mouth and then traveling to your ears. My vocal cords oscillate back and forth. It causes this disturbance in air, which travels outwards. But if I were to look at any one air molecule, it's not traveling from my mouth to your ears. It's just oscillating back and forth. So the medium does not travel with the wave. The medium, which is just what the wave is traveling through, just oscillates back and forth or up and down, but it doesn't necessarily, well, it doesn't move along with the wave. Okay, so what we were talking about in terms of the transverse waves, transverse wave is one in which the disturbance is perpendicular to the direction of travel of the wave. So if I had a transverse wave, you know, this wave might be moving to the right. But if I were to look at, let's say, any one piece of the string, as this wave moves by, the string is just oscillating up and down. So this would be a transverse wave. Types of transverse waves you probably have seen: wave on a string, water waves, and wave machine was just a sort of demonstration that I had to show you, but I didn't bring it back, unfortunately. And then on the other hand, a longitudinal wave. is one in which the disturbance is along the same direction or parallel to the direction of travel of the wave. So again, one more time, the two types of waves are transverse wave, which you see up at the top. The wave is traveling to the right. Any part of the string is just oscillating up and down. So this little red mark here is just showing you one little part of the string, and it oscillates up and down while the wave is moving to the right. On the other hand, the longitudinal wave, the disturbance, the slinky, if this were slinky, is oscillating back and forth, but that's also the direction of travel of the wave, which is to the right. All right, let me try something new. I think I figured out how to do clicker questions. So what I want to do is bring up, share screen. Let's do that again. Nope, sorry. Stop share. Whiteboard, lecture notes. Okay, clicker question. So I want to try clicker question using polls here. So let's look at question 1. It says, consider the following waves. A wave made by fans at sporting events. So if you haven't been to a sporting event, or, you know, as people are sitting down, everybody goes, woo! Waves made on the surface of a lake by water, music in an auditorium, and you can tell this is an old question, TV signals transmitting pictures. We don't really have TV being transmitted the way it used to be. But the question is, how many of the 4 are transverse waves? And what I want to try is meeting controls. Why can't I get this going? Zoom, meeting controls. Okay, I thought I had this figured out. Oh, breakout room, stop. All right, let me try this one more time. Stop share. I want to do a poll. So let me see if I can launch the poll and then share the screen again. Ah, sweet. So I don't know what this looks like at your end, but this is a anonymous poll clicker question. So hopefully somebody on your side, you can see a poll. Can people see a poll? Never tried this before.
Yes, we can see it.
Oh, excellent. So the question is, how many of the above 4 are transverse waves? So I set this up just as sort of a generic poll for any clicker question. At most, there are 5 choices. So take about 30 seconds. Out of those 4 different waves, how many of those do you think are transverse waves? And just so you know, this is completely anonymous, so that I don't know who's answering what. But yeah, take a second, and I have no idea. Somebody who sees the poll, what do you guys see, and where is it on your screen?
Mine just popped up. It just came in front of the screen that you shared with me.
Oh, good. And can you also see the clicker
Yes.
question?
Yeah.
Okay.
Yeah, mine just popped up as well.
Oh, good. Excellent. All right. I'll give people another 10 seconds, and yeah, throw in a vote. What do you think?
I got the clicker question, but I couldn't read the back, and then I couldn't unmute it, so I just kind of guessed because I couldn't read.
Okay. All right, let me end this polling. Kind of curious what is. So 50% of you say 2 of the 4 are transverse waves, 30% say 3. So 1, let's go through them. Waves made, and let me relaunch polling. Let's just leave that and that. So 1, draw. Waves made by fans at a sporting event. That is a transverse wave. So 1, what is the disturbance? The disturbance is just the people that are sort of standing up and down. In this case, you know, if I'm standing up and down, that's the direction of the disturbance is up and down, but the wave is sort of traveling across the stadium. So that would most definitely be a transverse wave. Music or waves at the surface, on the surface of a lake, that would also be a transverse wave. So, you know, if I imagine I had a wave that's traveling to the right, the disturbance, the water is just moving up and down, but the wave is traveling to the right. That would be a transverse wave. Music in an auditorium. Any form of sound is basically a longitudinal wave. And then TV signals transmitting pictures. So I wouldn't expect people to know this, but before cable, all TV signals are basically transmitted just like radio waves in a sense. Any form of electromagnetic wave is a transverse wave. So light is a transverse wave, radio waves is a transverse wave. So in this case, the actual answer was 3. Waves made by fans at a sporting event, waves on the surface of a lake, and TV signals transmitting pictures. And actually, well, I'll just touch on this one. Very similar. In class, I would have asked just one or the other. Which of the following are transverse waves? A, an ocean wave rolling towards Santa Cruz Beach. B, the sound of one whale calling another underwater. C, a pulse sent down a stretch rope by snapping one end of it. So in this case, 1, ocean wave, kind of like before, that's going to be a transverse wave because let's say the wave is moving horizontally, but the water is just disturbed vertically up and down. Sound of one wave calling another, nope, that is a longitudinal wave. A pulse sent down a stretched rope by snapping one end of it, yes, that would also be a transverse wave. So in this case, the answer was A and C. Okay. Okay, let's go to lecture notes again. Okay, so now what I want to talk about is how do we actually describe a wave? So like I said, if I had something like an object moving, if we were looking at Newton's laws, we might describe the object by the mass of the object, how fast it's moving, what direction it's moving, if it's accelerating, things like that. But for a wave, there's specific quantities that we talk about. And as a little preview, the 4 or 5 main quantities that we're going to be looking at are amplitude, which is in essence how big the wave is, wavelength, which in a sense is how long the wave is, frequency, which is really in a sense how many waves pass a given point in a given amount of time. And then in the end, we're going to look at the big thing is wave speed. So we're going to look at this for a transverse wave. So again, let me just draw this so I can be specific. Not bad. So 1, the amplitude is how high the wave is, how tall it is. And the way we define the amplitude is it's the distance from either the highest point. Let me do a different color here. Draw from the highest point to the middle, or from the lowest point to the middle. And actually, let me just be specific about the highest and lowest points. The highest point on a wave is called the crest. So it's just the very, very highest point on a wave, and the very lowest point is called a trough. Just so you know, some books call this, rather than a crest, the peak, and some books, instead of a trough, call it a valley. But your book is using crest for the highest point on a wave, trough for the lowest point. So here's the crest of a wave, here's the crest. Trough is the lowest point. The distance between the middle and the highest point, or the middle and the lowest point, is called the amplitude. Brian, question.
If this were to be like on a celebration or a quiz, and we were to like put down, or like a homework question, we put the other words you said, peak and valley, would it be wrong or?
100% wrong. No, it's totally right. No, I'm not specific about if you call it a crest or peak or trough or valley. So just keep in mind, crest or peak is the very, very highest point of a wave. Trough or valley is the very, very lowest point. And the amplitude is always the distance from the highest point to the middle or the lowest point to the middle. It should be the same. Now, let me just say it's not, and this is a mistake a lot of people make, it's not the distance from the highest point to the lowest point. That would actually be twice the amplitude. So amplitude, distance from center to the highest point, center to the lowest point. Wavelength, in a sense, is how long the wave is. It's the distance from crest to crest or trough to trough. So in this case, wavelength for this wave I've drawn would be the distance from, darn it, the distance from peak to peak, distance from trough to trough. Those should be exactly the same. So in this way I've drawn it, my wavelength is the distance from peak to peak. And for the wavelength, we use this symbol lambda. It's also the distance from trough to trough. And in fact, let me just show you, it's also the distance for one complete wave. So let me draw this one more time with different colors, blue. So there's really three different ways of thinking about the wavelengths. So one, it's the length for one complete wave. And one complete wave is when the wave goes to the highest point, back down to where it starts. So this right here is one wavelength. So this is one complete wave would be something like that. That distance is the same as the distance from peak to peak, which is the same as the distance from trough to trough. So there's really three different ways of thinking about the wavelength, and they're all the same. The distance from one high point to the next high point, crest to crest, the distance from one low point to the next low point, trough to trough, or the distance for one complete wave. And actually, let me do a new share. I think I have a cool site to show this. Traveling waves. Okay. Can I amplitude? Okay, here. So one, this is a longitudinal, I'm sorry, this is a transverse wave. You can kind of see the wave is traveling to the right. And this little dot here is just showing you one part of the string. So this string, this little piece right here is just oscillating up and down while the wave is traveling to the right. So that is a transverse wave. So here I can adjust the amplitude. So if I decrease the amplitude, that is just decreasing the height from the middle of the wave to the highest point or the middle to the lowest. So can I pause this? Oh, I can. So in this case, my amplitude would be the distance from here to here or the distance from here to here. It's always from the middle to the lowest point or the middle to the highest point. The wavelength is the distance from one peak to the next peak or one trough to the next trough. And if I increase the amplitude, or I'm sorry, if I make the wavelength, wave moving to the, continue. So here's a wave with a bigger amplitude. Here's a wave with a smaller amplitude. Here's a wave with a smaller wavelength. Here's a wave with a bigger wavelength. Okay, let's go back to this again. So let me just pause real quick. Any questions so far on just transverse waves, longitudinal waves, wave description in terms of highest point is peak, lowest point is valley, amplitude is the distance between the middle of the wave to the highest or middle to the lowest, wavelength in a sense is how long the wave is. There, just a second, see if anybody has any questions. Tristan, you got a question? No, I just saw you. Okay. If not, moving on. Okay. So looked at amplitude, looked at wavelength, frequency. I can't really draw frequency on a picture of a wave. What it is one, every wave is made by some object which is oscillating back and forth. How many times that oscillation happens every single second is called the frequency. And we measure frequency in hertz. And it ends up that 1 hertz is the same thing as basically 1 vibration or oscillation per second. So if I have an object, let me do a new share again. Let's go back to this. No spring mass. So here I can't really vary this very much, but this thing is oscillating up and down. If I counted how many times it oscillated up and down every second, that would be its frequency. So like right now, this looks like it's maybe oscillating up and down maybe once a second. Its frequency would be 1 hertz. I can't, oh, if I change the mass of the block, reset. Go. I don't need that. So here, this is something with a smaller frequency. It's not oscillating up and down as rapidly. So the number of oscillations that happen every second is less. If I decrease the mass of this block, and now can I do it? Get rid of this circular motion. So this is oscillating up and down more frequently. So it would have a greater frequency. Okay, let's go back to that. So frequency is how many times whatever's producing the wave is oscillating up and down. But the other way of thinking about it is it's how many waves pass a given point in every single second. So if I were to just stay in one position and count how many waves pass by me every second, that is the frequency of the wave. And kind of interesting, FM and AM stations. Once we get to electromagnetic waves, I'll talk about radio waves a little bit. But one thing I wanted to mention is all radio waves are basically produced by an antenna. And in the antenna, you have these electrons which are oscillating up and down. The frequency that the electrons oscillate up and down at is the frequency of the radio wave they're going to produce. And AM and FM stations actually have unbelievably high frequencies. So you may not know this, but AM, any AM station is actually in what's called kilohertz. And I don't even know an AM station, but let's just say, does anybody have an AM station that's popular? I don't even know. Let's just say you had something that was 1040, well, 95.7 FM. What's a AM station? I don't know. Let's just say you had 104. I'm trying to think. I don't know of any AM stations. But anyway, if you had an AM station that was 104, that's actually 104 kilohertz, which means that the electrons in the antenna of the radio station that's producing the radio wave would be moving up and down. 104 kilohertz is 1,000 times, so it would actually be moving 104,000 times every single second. FM is actually in megahertz, which is 1,000,000 hertz. What's KPIG? 105.7? So like 105.7 FM.
102.5 kDON.
102.5, we'll use that one. So what was I saying? This one I just said was like 104 AM. But not, what did you say? What was it? 102.5? 102.5 FM? So this is actually really 102.5 million hertz, which is really amazing. And I'll show you an animation in chapter 20. But that means the electrons in the antenna that's producing the radio wave, that's 102.5 FM. The electrons are oscillating up and down 102.5 million times every single second. Crazy, right? So imagine trying to move your fingers up and down 102.5 million times every single second. That's what's happening in the antenna that's producing that particular radio wave. Pretty interesting. Okay, so amplitude, height of the wave, wavelength, how long the wave is, Frequency is how many waves would be passing a given point every single second. And the last one besides wave speed is period. Period is how long it takes for one complete oscillation or one complete up and down motion. So period is a time, and we measure it in seconds. So, you know, some wave is being produced, let's say, by just me moving a string up and down. I'm producing a wave on a string. Period would be how long it took for one complete oscillation in seconds. So if I was moving my hand up and down and it took me 2 seconds to make one complete oscillation, the period of the wave I produce would be 2 seconds. And it ends up that period and frequency are inversely related to each other, meaning frequency is equal to 1 over the period, and period is equal to 1 over the frequency. And this kind of makes sense if you think about it. If an object had a frequency of 2 hertz, that means it's oscillating up and down 2 times every single second. Well, if it's oscillating up and down 2 times every second, how long does it take for one oscillation? Half a second. Or let's say that the frequency of something is equal to 10 hertz. That means every single second it's oscillating up and down 10 times. If that's the case, how long does it take for one oscillation? And in this case, the period would be 1 over 10. It would be 1/10 of a second. So frequency and period are related. They're inversely related. Frequency is 1 over period. Period's 1 over frequency. So now for the big giant equation, which holds true for every kind of wave that you can consider. And the giant big equation is this. Well, one, I know in general speed is a distance divided by a time. If I'm talking about a wave, how far a wave travels in a certain amount of time, I can use just the definitions of wavelength and period. So wavelength is really how long the wave is. Period is how long it takes for one complete oscillation. So in essence, a wave travels a distance of the wavelength in one period. And actually, let me write that. That's good. A wave travels a distance of one wavelength in one period. Period is just how long it takes for one complete oscillation, which would be how long it took for one wave to pass by. The distance it travels is the wavelength. So wave speed equals wavelength divided by period, but 1 over the period is the frequency. So this right here, wave speed equals wavelength times frequency, is a gigantically important equation for waves. So just to be specific, because you might see this in some books, for wave speed, we use V. For wavelength, we use this symbol lambda, and for frequency, we use F. So how fast a wave is moving in meters per second equals the wavelength in meters times the frequency in hertz. So I have a clicker question or two about this. So big equation, and let's just do a new share. Go back to this types of waves. So again, one more time and stop this. Height of the wave, the highest point is called the crest. Lowest point is called the trough. Distance from peak to peak or from trough to trough is called the wavelength. The distance from the highest point to the middle or the lowest point to the middle is called the amplitude. And how fast the wave moves. So let's say I was right here and let's say I wanted to know the wave speed. It's really how fast this whole wave is moving to the right. So if I, had a radar gun and I could somehow time how fast this wave is moving, that's the wave speed in meters per second. And for any wave, wave speed is going to be related to both the wavelength and the frequency. And the equation is wave speed in meters per second equals wavelength in meters times frequency in hertz. So here is a clicker question that you will most likely see some form of again. So this is sort of an interesting question. So question 4. So let me read it first. I'm going to stop this share, start a poll, and then bring this back up. If the frequency of a wave is doubled, what change occurs in its speed and in its wavelengths? So we know wave speed equals wavelengths times frequency. Oh, that's horrible. Or wave speed equals wavelength times frequency. So now the question is, what happens if I double the frequency of a wave? How's it going to affect its wave speed? How it's going to affect its wavelengths? So let me stop this, bring up a poll, relaunch polling, continue. Now I can do screen share, go back to this. All right. So this is an interesting, somewhat challenging question conceptually, but if I double the frequency of a wave, how does that affect the wave speed? How does that affect the wavelength? Take about 20 seconds, think about that, and then when you have a decision, please use the poll to just put in, what do you think? A, B, C, D, or E? What happens to its wave speed? What happens to its wavelengths? Don't be afraid to vote. We only got 2 out of 14 voting. Throw up a vote. What do you think? And I'll tell you what, I'm going to give you a hint. The answer is not B. Why can I draw?
I still can't vote for some reason. But
Can't vote?
yeah, I don't see the poll. I don't know.
And for most people, the poll just popped up.
Yeah, no, it didn't pop up for some reason.
Yeah.
I'm also on my phone, so it like covers the whole screen. So I
Oh, yeah. So yeah, if you're watching this from your phone, it's probably not, you're not going to be able to vote, I think.
Yeah, I was able to vote, but I just couldn't see the questions because it was blocking the thing, and then I couldn't like press the mic so that you could read them out because it's just locked on the screen. So.
And I'm also noticing that I've been helping people with Zoom on iPads and PCs and Mac, and every Zoom client's slightly different. So Zoom on your phone might look slightly different than Zoom on your PC and things like that. All right, well, let me just end this, and we had a little bit of everything. D, remain the same. Ooh, so the correct answer is D. And I want to talk about this because this is an interesting concept. So 1, let me ask you a question. What's the difference in, if I'm listening to music, what's the difference between the sound a guitar makes or the sound that the drums make or something like this? Well, without going into all the physics of music, all the different instruments are producing sounds of different frequencies. If those different frequency sounds traveled at different speeds, then all of the instrument sounds would arrive to you at different times. So if the higher the frequency, the higher the wave speed, then sounds with a high frequency would reach you at a different time than sounds of a lower frequency. Or once we get to light, what's the difference between red and green and blue and so on? Light is just an electromagnetic wave, and the only difference between red and blue and green, different frequencies of light, different wavelengths of light. So if different waves, if light of different frequencies traveled at different speeds, then when somebody walked into a room, you might see their hair before you see their eyes, or you might see their shirt at a different time than their hair, depending upon the frequency. That's not the case. So this equation wave speed equals wavelength times frequency makes it look like that if I were to double the frequency, then this wave speed would double. Mathematically, that's what it looks like. But the end result is this wave speed is a constant that only depends upon the properties of the medium that the wave is traveling through. So for example, sound, the speed of sound depends upon temperature. At a given temperature, all sound waves will travel at the same speed, which means that if the frequency goes up, the wavelength has to go down. So let me go back to this. Oh, I'm over here. Lecture notes. Stop.
So in terms of temperature, would that mean like heat would make it go faster?
It ends up that for sound, the higher the temperature, the faster the speed of sound. So speed of sound depends upon temperature. So like right now, I don't know what the temperature is, but the speed of sound is around 700. The speed of sound is around 750 miles an hour. All sound waves at the temperature it is today would be traveling at 750 miles an hour. So let me just go to this for a second. So in this equation, wavelength times frequency equals wave speed. And again, I'll just write it out. So wavelength times frequency equals wave speed. This wavelength, let me draw this a different color. This is only depends, whoa, that's horrible. Only depends upon properties of the medium. So only depends on properties of the medium the wave travels through. So like I said, for sound, the speed of sound depends upon temperature. It also depends upon humidity and a couple other things, but mainly it depends upon temperature. At a given temperature, all sound waves will travel at the exact same speed. Now, what determines the frequency of a wave? Here's a good question. What do you think determines the frequency of a wave? All waves are created by something which is oscillating up and down or back and forth. Like I said, for sound, me talking, it's my vocal cords oscillating back and forth. The frequency that they oscillate back and forth at will be the same as the frequency of the sound wave they produce. So frequency is determined by frequency of the oscillating object that produces the wave. So wave speed is fixed. Whatever medium the wave is traveling through is going to determine the wave speed. For light, it has to do with certain properties of the material. We call it the index of refraction. For sound, it depends upon temperature. At a given temperature, all sound will travel at the same speed. The frequency of the sound wave is going to be determined by the frequency of whatever is oscillating back and forth to produce the sound wave. And basically the wavelength, and if you're a mathematical person, the wavelength is just determined by the wave speed divided by the frequency. So whatever's producing the wave determines two things: the amplitude of the wave and the frequency of the wave. So if I want to produce a wave with a low amplitude, I would just oscillate whatever I'm doing, not very much. If I wanted to produce a wave with a high amplitude, I would oscillate my wave much more. How frequently I oscillate is going to determine the frequency of the wave. So a low frequency wave is one that's not oscillating very quickly. A high frequency wave is one that's oscillating much faster. So for sound, the oscillating object for voices are vocal cords. If I'm talking about a musical instrument, it might be a string oscillating back and forth, or the surface of a drum oscillating back and forth. All right, let me pause for a second. few things we went through. So the description of a wave, important things: amplitude, wavelength, frequency, period, wave speed. Big equation that applies for all waves is wavelength times frequency equals wave speed. This equation makes it kind of look like that if I were to change the frequency of a wave, I would change the wave speed. But that is not the case. The wave speed only determines, the wave speed is determined by properties of the medium. So if you increase the frequency, the wavelength decreases, but the speed does not change. For those of you watching this live, I'm most definitely going to ask some sort of question about this on the next quiz and possibly on the next celebration. So if the frequency goes up, the wavelength goes down, but the wave speed doesn't change. If the frequency goes down, the wavelength goes up, but again, V doesn't change. So, summing it all up, bigger frequency, smaller wavelength, smaller
Can you go
frequency.
back up? Can you go
Yep.
back up? And just pause for a second, please.
Yes. Okay. Questions I can answer about anything I've covered so far.
Slightly unrelated, but how are the celebrations going to work online?
So these celebrations are just going to be like a longer quiz. And so people have been doing okay on the quizzes. My thought is it's just going to be something like 30 or 40 or 50 multiple choice questions. It'll be somewhat evenly, it'll probably be evenly. So it'll be on chapter 22, 23, 24, chapter 19, and 20. So you're going to have 5 chapters. Probably just going to be 50 multiple choice questions that I'll give you a couple hours to do. But it'll be just like the quiz, is only longer. So there won't be any short answer questions. It's just going to be multiple choice, and it's going to be fairly straightforward. I'm not trying to trick anybody. I want everyone to do well. So I'll make a video sort of talking about the celebration as we get closer to it. But it's just going to be multiple choice, and it's going to be done through Mastering Physics. Booyah. Other questions? If not, I want to cover one other, let me see, I have interference, Doppler effect, standing waves. Perfect. Okay. So last thing I want to talk about today is interference. And I want to start with a question. Yes or no question for you. Can these 2 pens exist at the same place at different times? Yes or no? And the answer is yes. Pen is here. Now this pen is here. Both pens existed at the same place at different times. Can these 2 pens exist at different places at the same time? Of course. These
Would
2
you just be moving it back and forth? Oh,
What's
wait,
that?
Oh, you have 2. I thought you only had 1.
No. Yeah, they're kind of hard to see. But yeah, we'll just stick with that. So these 2 pens can exist at different places at the same time. These 2 pens can exist at the same place at different times. But the question is, can these 2 pens exist at the same place at the same time? And the answer is no. Physical objects that have mass that take up some kind of volume obviously can exist at the same place at the same time. However, waves can. So material objects can't exist at the same place at the same time, but waves most definitely can. And the fact that you can pick up, God, I don't even know, what, maybe 50, 60, 70 different radio stations on your radio. What that means is you have 50, 60, 70 different radio waves existing at your antenna at the same time. And all you're doing when you're changing your radio station on the radio is you're preferentially picking out one of those 70 or 80 different radio waves that are existing at the location of your antenna. Here's the interesting thing. When two waves do exist at the same place at the same time, they can do what's called interfere with each other. And the interference can result in either getting a bigger wave, which is what we call constructive interference, or a smaller wave. And in this case, you can actually what's called have complete cancellation, called destructive interference. So let me show you a little animation showing that. Interference. Okay, let me pause, reset, play. Okay, so what you're seeing here is you've got a wave on top here, which is moving to the right. I've got another wave, which is moving to the left. And down at the bottom is the two waves added together. So when the two waves, like right now, they're not at the same place at the same time. But if I let this play, what I would see is now these two waves are existing. So one, it's showing them on top of each other. I have no easy way of showing you two waves that are at the same place at the same time. But imagine instead of being one on top of the other, these guys are moving exactly towards each other. Well, when they are at the same place at the same time, in this case, they're doing what's called constructive interference. The end result is a bigger wave. So if I wanted to know what is the result, keep in mind a wave is just a disturbance. And so what this bottom wave is showing is all I'm doing is adding these two waves together. So like right now at location 5, and don't worry about the numbers, but this is just where the wave is. The height of this wave is about 20. The height of this wave is about 20. So I add them together and the height would be 40. We call that the principle of superposition. You don't need to worry about it mathematically, but all you're doing is you're just adding the two waves together.
So
And
what way
then-
does it start to go? Like,
Say that
what does it matter? Like the direction, like here, like the red one's going like from left to right, and the blue's going right to left, and then they like and the
No,
one
so
where
as
they
long as I had, and it doesn't matter, they don't have to be traveling in opposite directions either. I could have, you know, one wave overtaking another wave if it's moving faster. And then as long as they're in the same place at the same time, I'm just looking at how do I add these together? And it's really just adding them mathematically. So let's do the other one, identical pulses, destructive interference. So in destructive interference is when basically when one wave is peaking, the other wave is at a minimum. So they're at the same place at the same time, but in a sense, they're like mirror images of each other. So now if I let this go, oh, can I step back? So here you can see that when the red wave is at its very maximum, the blue wave is at its very minimum. And again, mathematically, to figure this out, you would just add them. So like here, at this location 5 again, this red wave is at a height of 20 centimeters. This blue one is at negative 20. I add these together, and the end result is they cancel each other out. So going back to this, so let me just kind of go over to here. So I have no easy way of drawing two waves at the same place at the same time. But let's just say that I had this wave. So we're going to add these up. And let's do this in a different color, draw. So let's say that I had a transverse wave and I had another identical transverse wave. And these two were at the same place at the same time. Now, again, I can't easily draw two waves at the same place at the same time, but imagine these two waves existing at some point in space at the same time. I add these two together, and what I'm going to get is a wave that has the same frequency, the same wavelength, but the amplitude is going to be twice as much. So in this case, the sum of these two waves would be a wave which has a bigger amplitude. This is what we call constructive interference. If we were talking about a sound wave, the result of constructive interference would be a louder sound. If we were talking about an ocean wave, the result of construction of interference would be a much taller wave. What I would have shown you, and unfortunately, again, I can't, is I would have played 2 sounds out of speakers in the classroom and had you walk around the classroom. And you would find regions of the classroom where you have constructive interference, and it'd be a much, much louder sound there. But then if you move to a different spot of the classroom, you'd find spots where you hardly hear any sound at all. And that's because we're not having constructive interference, but we're having destructive interference. So in destructive interference, same situation as before. So imagine I've got these 2 waves. Come on, that are at the same place at the same time. And I'm adding them together. Now, for constructive interference, they're both peaking at the same time. They both have a minimum at the same time. When I add them together, I get a wave that has twice the amplitude. For destructive interference, in a sense, the waves are mirror images of each other. So if one wave looked like this, and the second wave existed at the same place at the same time, that doesn't look very good. So when this wave is at a maximum, this one's at a minimum. What I'm trying to draw is this, that when one wave is at the maximum, the other wave is at the minimum. So like here, this one is at a maximum here, while this one's at a minimum here. This one's at a maximum here, while this one's at a minimum here. If I drew, you know what, I'm gonna draw this one more time, this sucks. Oops, all right, draw, red. Draw, green. All right, so I'll just make it easier. So one wave looks like this. The second wave looks like that. So they're identical waves, but when this one is peaking, this one is at a minimum. When this one's at a maximum, this one's at a minimum. If I were to add these 2 waves together, what I get would be complete cancellation. So this is just me sort of drawing nothing. This is called destructive interference. If we were talking about sound, the result, if you had completely destructive interference, would be no sound at all. So if anybody has a nice set of noise canceling headphones, just real quick, how do they work? All noise canceling headphones actually have a microphone on them also. What happens is the microphone is recording the external sound, and then there's some kind of circuitry inside the headphones that basically take the sound that you heard and then in a sense flips it upside down so it looks like the mirror image, and then sends it into your headphones at the same time as you're hearing the external sound. So what you're hearing is, this might be the sound from outside. This is your noise canceling headphones taking that sound, flipping it upside down, and then sending it into the headphones at the same time. So you're hearing the external sound and in a sense the mirror image of it at the same time, producing what's called destructive interference. Kind of cool. And just, you don't really need to know this, but superposition principle is the name we give to the fact that if I want to know what is the result of 2 waves at the same place at the same time, I just add these disturbances together at every point. Meaning, if I want to know what is the result at this point right here, I look at both waves and I add them together. So at this point, this wave has a certain disturbance. This wave has a certain disturbance. The sum of these 2 is going to be something that has twice the amplitude. Whereas, let's say I want to look at what is the result of the wave right here. Well, this one's at a maximum. This one's at a minimum. I add these 2 together. and I get complete cancellation here at every single point. So like right here, if I look, this one's at a minimum, this one's at a maximum, they cancel each other out. So constructive interference, big thing, keep in mind, is I end up with a bigger amplitude wave. And for destructive interference, I can actually end up with complete cancellation. Fortunately, I don't have the equipment, but this can also happen with light, which is really, really cool. So if you were to continue on with physics, at some point you would do an experiment called the double slit experiment. And you can send light through 2 different slits. And when the light meets at a certain spot in space, that light can undergo interference. And if it's constructive interference, what you would end up with is a really, really bright spot. If you had destructive interference, you could actually end up with the light canceling each other out and have complete and utter darkness. Pretty damn cool. All right, let me see if I have a clicker question for you. Oh, let's do one more. Let's end on a clicker question. And let me just try this polling one more time. So one, let me just stop this share, open up a poll, relaunch polling, continue, screen share, clicker question. Okay, so this is question number 5. And it says, if you dip your fingers repeatedly into water and make waves, you dip your fingers repeatedly into water and make waves. If you dip your finger more frequently, the wavelength of the waves will increase, decrease, or stay the same. So, you know, I'm making waves just by dipping my finger. Now I dip my finger more rapidly. How does that affect the wavelength of the waves? Increase, decrease, or stay the same? What do you think? Take 25 seconds. If you can see the poll, make a choice. What do you think? Wavelength, how does it affected when I increase the frequency of the waves that I produce? And the answer again is, remember that if frequency goes up, wavelength goes down. If frequency goes down, wavelength goes up. So in this case, I am the person who's creating the waves, and the frequency that I dip my fingers in the water at is going to be the same as the frequency of the waves that are produced. So if I dip my finger more frequently, frequency goes up. If the frequency goes up, the wavelength has to go down. So the correct answer is wavelength decreases. Okay, I'm going to end this polling. Stop this share. It is 10:38. Oh, 9:45. Oh, it's supposed to go to 10:30 and then have some office. I'm totally losing my brain. Let me hold on for a second. Online resources. What's today? Lecture to 10:15. 10:15 to. Anyway, I went over a little bit for the lecture. Rather than stopping this Zoom and then restarting it for office hours, I'm just going to sort of roll right into it. So we are done with the lecture portion of today's Zoom. I will stick around for another 20 minutes and answer any questions if people have specific questions on what I just covered. If not, I'm going to post this to YouTube, hopefully by tonight, if not by tomorrow. Thank you for those of you who attended live. Thank you, Tristan. Thank you, Brian. Thank you, everybody. If you have any questions, let me know. I'll stick around. I'm just going to sort of pause the video. Well, no. Well, yeah, I'm going to pause the video. So if you have questions, I'm going to stick around. If not, thank you for joining, and hopefully I will see you all on today, Thursday. I'll see you on Tuesday.
I have a quick question.
Yeah, Jamie, what's up?
I was just curious. I remember you mentioning last week about posting the OneNote.
Yes.
I can't find it.
Okay, let me go to. Okay, so on your online sort of resources page, which I added to your main Physics 10 webpage. So just a few things that are just useful. I'm always going to sort of have your schedule of what's due this coming week. This is just the basic office hours lecture schedule. So I will add the lecture notes for chapter 19 and 20. I haven't added that yet. But down at the bottom, Microsoft OneNote notebooks used for Zoom lectures. So I haven't linked the one yet for chapter 19, but you need to have OneNote, obviously, to access them. But I'm also posting PDFs of the files once I'm done. So like chapter 24, if you do have OneNote, you click on it, and then it will actually open up the OneNote. And it's got all of the different sections that I was, let me just make sure this opens up.
Okay, I found it.
You got it? So yeah, it's got the lecture notes and all of that. And just so you know, these are updated at the end of every lecture. So like once I post the one for chapter 19, once I'm done lecturing, it'll update. And then the PDFs I will post once I'm done a chapter.
Perfect. Okay, that's all.
All righty. So I'm going to pause.
Thank you.
Allie.
Just thank you.
Oh,
I'm
thank
gonna
you,
go.
Allie. Have a wonderful weekend.
You too.
Thank you. I appreciate it.
All right, take care, Laura. All right, I guess that is it. I'm going to pause recording, see if anybody comes in.